Okay, it's logarithm part video part 6, and I think so. It's video part 6. Let me check again. It's video part 7. It's video part 7 now. Let me start with limits. Limit of ln x as x approaches plus infinity is ln plus infinity, which is infinity. Ln infinity is infinity. This one is okay. Limit, these infinities we should know before we start doing the graphs. This is very important video now. Limit of ln x as x approaches 0, it's ln 0, and it's minus 1. Now you will see when we draw the limit, the ln x, right? It's going to be something like that. Ln x is going to be something like that. As x approaches 0, from the right, this will approaches negative infinity. And when it approaches plus infinity, it will approach also plus infinity. This means limit of ln x as x approaches infinity is infinity. And when x approaches 0, it's minus infinity, plus infinity, minus infinity. As x plus infinity, it will be plus infinity. And as x minus infinity, as 0, as abscissa approaches 0, the function will approach minus infinity. Limit of ln x over x power n is equal to 0. You have always to know that, and I will tell you how now. And limit of x ln x as x approaches 0 is always equal to 0. And why is that? Let me explain. If we substitute instead of x infinity in the part 3, right? Limit as x approaches plus infinity of ln x over x to the power n, where n is a natural number or whole number. Natural number because some countries they consider that n natural means starts from 0, or some countries they start with 1, not with 0, and they consider that whole number starts with 0. Whatever. Limit of this function at ln x over x power n as x approaches infinity. Why it is equal to 0? Because it's simply ln plus infinity, which is over also plus infinity instead of x to the power n. This is infinity over infinity, and infinity over infinity is what? Is indeterminate form. And when we have indeterminate form, we can use the Hopital rule, right? The Hopital rule. Hopital rule gives me the same limit, right? We keep the same limit, but we derive not the function. We derive the numerator alone over denominator alone. What is the derivative of the numerator alone? What is the derivative of ln x? It's simply 1 over x, right? And what is the derivative of x power n? It's nx to the power n minus 1. Now, if we substitute infinity, we are going to get this. We can rewrite it as 1 over n, right? We multiply this down. It will be n into x to the power n minus 1 plus 1, so it's x power n again. The answer is going to be 1 over, if we substitute infinity now, this is limit, as x approaches infinity. If we substitute infinity, it's going to be 1 over infinity, and 1 over infinity is equal to 0. Same for part 4. Its limit of x ln x as x approaches 0, it's also equal to 0. If we substitute directly, it will be 0 into ln 0. Ln 0, it's minus infinity, right? We just found it over here. And 0 times negative infinity, it's indeterminate form, so we change form. We write it as limit of ln x, right, over, we write it as limit of ln x over 1 over x. X is 1 over x. The reciprocal of x is x, as x approaches 0. And now we substitute. It's going to be also negative infinity over 1 over 0, positive infinity, right? So the answer is going to be also indeterminate. And since it's fraction and it has indeterminate form, we can use the Hopital rule. Hopital rule is to have the same limit, right? But derivative of the numerator, which is 1 over x, over derivative of the denominator, which is minus 1 over x squared. So the answer is going to be minus x squared over x, multiplying the extremes and the means, right? It's going to be limit, as x approaches 0. If we simplify, it's going to be limit as x approaches 0 of minus x. And now substitute 0, it's going to be 0. So those are very useful and important limits to to know. Find the following limits. Let's do some more limits. Let's do some more limits after I clean up the board. Okay. Let's find some more limits. What is limit of ln x squared as x tends to 0? Okay, this is easy because directly we can substitute 0, right? It's ln 0 squared, so it's equal to ln 0, and ln 0 is equal to minus infinity. It's an answer. Also this one, we can substitute directly ln, right, plus infinity square, which is plus infinity. So the answer is plus infinity. It's also simple. All right, let's see this one. Ln x over x squared as x approaches 0. It's ln 0, right? If we substitute, it's ln 0 over 0 square, right? Over 0 square, which is 0. And x approaches 0, which is 0 plus, right? 0 plus. So ln 0 is minus infinity over 0. Negative infinity over 0 plus is plus infinity. Is minus infinity, sorry. Is minus infinity. And we can use the... This is not minus infinity. As x approaches 0, right? As x approaches 0. This is not the same as... It's not the same as what we have here. What we have here is ln x over x power n, which is x power 2 here. But this as x approaches plus infinity, that's why it gives us answer equal to 0. This one, the answer is negative infinity over 0 plus negative infinity if we divide it over a very small number. So the answer will be negative infinity. All right, let's see as x approaches 0 now. As x approaches infinity, I mean. As x approaches infinity, we said it's directly we can put it equal to 0. That's what we said in rule part 3 here. Ln x over x power n as x approaches infinity. Also, we can prove that because limit as x approaches plus infinity of ln x power n, sorry, of ln x only over x power 2. So it's ln plus infinity, which is infinity over infinity square, which is infinity over infinity. It's indeterminate. Again, I can use what? Hopital rule. Hopital rule tells us it takes the same limit, but we just find the derivative of the numerator over derivative of the denominator. So the answer is going to be limit as x approaches plus infinity of 1 over 2x squared. Now substituting instead of x plus infinity, it's going to be 1 over infinity. The answer is equal to 0, or we can write it as 0 directly. We still have some more time. Let's do some more problems about limits. Let's take limit of ln x radical 1 plus ln x squared as x approaches 0. As x approaches 0, if we substitute 0, it's 0 times whatever here inside is ln 0 infinity. So 0 times infinity is indeterminate. So what we do is we have to rewrite this as limit as x approaches 0, which is 0 plus, of radical of the limit ln, sorry. It's I think so. It's not ln of. It's ln of. It's limit directly. It's limit directly. This one here, it shouldn't be ln. This one here should be just limit directly. Ln only inside, right? So it's radical 1 plus ln x to the power 2 over 1 over x. We convert the x as 1 over x. So what is the answer? It's limit as x approaches 0. If we substitute 0, it will be infinity over infinity, so which is undefined. So let's use Hopital over here. So Hopital rule says we take the limit as x approaches 0 of the derivative of the numerator. What is the derivative of radical u? It's u prime. It's u prime over, it's u radical u. It's u prime over 2 radical u. This is 2 radical u. 1 plus ln x all square. What is the derivative of ln x square? Derivative of ln x square, it's 2 times ln x to the power 1 times the derivative of ln x, which is 1 over x, divided by the derivative of the denominator, which is minus 1 over x squared. So the answer is going to be, if